Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept regarding net positive suction head. So in our last lecture, we have discussed about the cavitations, how the cavitations formed and what is the effect of cavitations and how to avoid the cavitations. So we've discussed in that. Along with this, in the centrifugal pump, also we'll discuss about the net positive suction head. So net positive suction head actually, basically this concept is to use to avoid cavitation. Okay, this concept also is used to avoid cavitation in the pump, to avoid cavitation in the pump. And this concept actually is most commonly used in the pump industry. Most commonly used in the pump industry because it is very much essential in the to identify the cavitations value. So we know that what is the effect of cavitation. If cavitations are formed, how much losses can be happen. So we'll try to always avoid the cavitation in the pump. So the NPSH is nothing but the net positive suction head. So the net positive suction head is nothing but this is the measurement of pressure. Okay, this one I can say this is the measurement of pressure, that how much pressure is present at which point at the pump inlet. So this is the measurement of, we can say, pressure, or we can say how much pressure is available at the pump inlet. Measurement of pressure at the pump inlet. Once you identify this, how much pressure is present at the inlet, then we can assure that whether that water or liquid can be avoided from boiling, or we can keep the liquid from boiling. So to avoid this boiling, why to avoid the boiling? Because we know that once you identify the pressure value at the inlet of the pump, then we can assure that whether the pressure value is more than the atmospheric pressure or more than the vapor pressure or not. Once you will identify, then we can assure that whether this water or liquid is going to boil or it can be safe. That is our intention. So how the pump is working, that I'll just give a brief idea so that you can understand. Suppose this is our pump is there, and that in the pump we know that we have a eye is there in the pump, impeller eye, and in the impeller we have number of blades are connected. So these are the blades which are connected in the impeller, and this one I can tell this is our suppose pump, and this is the impeller one, which consists of number of blades, or blades are mounted on this impeller. And the pump is how it is, like this will be our pipe which will connected to this one, and this point is actually eye. Okay, this is our actually eye of the impeller, and in that again we have a shaft will be there. The shaft will be connected to the motor, and this pipe, that pipe I'm giving a line type, and this pipe will be connected to the sump level or to the reservoir. This is our sump level. Okay, this is called sump, or we can say it is a reservoir of liquid or fluid. So in the sump level, a pressure is working, that is P atmospheric pressure, that is called P atmospheric. That means atmospheric pressure is giving impact on this, that's why it is called P atmospheric. So the water need to be taken from the sump to the eye, or to the, you can say, inlet of the pump. This is our actually inlet of the pump, and this is nothing but this is the suction pressure or suction pipe. Actually suction pipe, through the suction pipe this water is to lifted up, and here it will have a like we have a like valve type will be there, that is actually called this is we used to call this is foot valve. Okay, this is called foot valve, and another one strainer will be there, the strainer for filtering the equipments. Foot valve and strainer both are connected at the end of this pipe, so that the water will be can be strained, and there will be no other accessories can enter to these pipes. So this is the suction pipe. Through the suction pipe the water will come inside, and after it's striking to this vein, then it will be this water will be come out from this, and it will go through the help of delivery pipe to outside. This is delivery pipe, and this will be supposed to go out. So here the thing is, as I told you, this is our P atmospheric. Okay, this is our P atmospheric, and at this inlet of this pump, when the pump started, how the pump will be started? So here shaft is there. The shaft will be connected to the motor here. So here we will have a motor, and this is nothing but shaft is there. So shaft will be connected to the motor. Once you switch on the motor, the shaft will be rotated. Once shaft will be rotated, the impeller is mounted on the shaft, so impeller will start rotating. Once this impeller started rotating, so due to this rotation, here at this point, at the eye of the impeller, our negative pressure will be created. Okay, negative pressure will be created, or you can say that is vacuum pressure will be created on eye of the impeller, we can say, on the eye of the impeller. So due to this negative pressure which is created, and here what will happen, here we have the liquid which is present, the atmospheric pressure value. So here the atmospheric pressure value, so we have this atmospheric pressure value, so which is more than the vacuum pressure, which is more than the P vacuum. So P vacuum is nothing but this one, where the at this point created. So the water will start lifted up, the water will be started lifted up from this pump sump level to the pump. Okay, now we need to see whether this pressure value is only up to a vacuum pressure is there, or whether the pressure is reduced in such a way that which is more or less than, like you can say, another pressure will be there, that is vapor pressure. So that is vapor pressure, you need to keep in mind. So vapor pressure of liquid is there. So which liquid is to be lifted up from here? So we need to identify how much vapor pressure is there for that particular way. Suppose we'll consider water is lifted, need to be lifted up from this point. Okay, from the sump level, the water is supposed to be lifted up, and we know that, okay, water is having the boiling point. So water is supposed to be boiled at 100 degrees centigrade. So 100 degrees centigrade, the water is supposed to be boiled at 1 bar pressure. At 1 atmospheric bar pressure is there. Now this vapor pressure actually, which is less than the vacuum pressure also. Even now we need to identify in the what is the role of NPSH here. Actually, the role of NPSH is nothing but to identify the height, the suction height, how much is there, and whether the pressure at this suction inlet of the pump is okay or not, or whether it is it is more than the vapor pressure or not. Because if it is less than vapor pressure, then the water started boiling. How it will boil, I'll tell you here. Okay, so the NPSH, what I told you, this is the measurement of pressure. Okay, this is the measurement of pressure of what? Of the liquid at the pump inlet, to keep the liquid from boiling, to stay away the liquid from the boiling. As I told you that we know that water will start boiling at the 100 degrees centigrade, but at that point we'll have the pressure of 1 bar. Okay, and here if I change the pressure here, the pressure value, if suppose I'll make it to 2 bar, then the water also won't boil at the 100 degrees centigrade. The boiling temperature of this water also will be going to be changed. So that may be 150 degree or 130 degree or 120 degree, some value will be there. Similarly, as you can see that we are increasing the pressure value, and here boiling point also, the boiling temperature also is changed. Now here if you reduce the pressure value here, so the boiling point or boiling temperature of this liquid also going to be changed. So here if I reduce the value of 1 bar pressure, from 1 bar pressure to suppose 0.5 bar pressure. Okay, so at the 0.5 bar pressure, obviously the temperature of boiling point of this water is going to also change. So it may be suppose 30 degrees centigrade. At 0.5 bar, the water is going to be boiled at 30 degrees centigrade. Now we need to identify in this, like when it is the pressure is changed, we need to check it how much the pressure value. That's why I told you that it is the measurement of pressure at the inlet condition. That we need to check it whether the pressure of this liquid is like atmospheric pressure or vacuum pressure, or whether it is vapor pressure is there. So that we need to check. Otherwise, if it is the pressure value is like a vapor pressure is there, that means vacuum pressure is very, very less, and it is less than the vapor pressure value, then at that point what will happen? The water will start boiling. That means low pressure created. Even temperature will be there same, but temperature of what? Normal temperature is there 30 degrees centigrade. So the water will be lifted up here 30 degrees centigrade. So even in the 30 degrees centigrade also, the water started boiling. Once the water will start boiling, then we know that we'll have the bubble formations will be there. Once it will started boiling, then the water will be started, bubble formations will be there. So the bubble formations, once the bubble formations will be there in the pump, see, this is the low pressure zone. We can say vacuum pressure zone. That means low pressure is there here. Now when it will cross this pump, like when it will, after striking here, it will go out from the impeller. Okay, when it will go to this casing and impeller, it will exist from the pump. At this point we have the high pressure zone. Okay, so when this bubble will move from low pressure to high pressure zone, then due to this high pressure, these bubbles are going to, okay, the bubbles are going to blast. Okay, so due to this blast or expansion of this bubble, that will give a impact on the all this, you can say, the pipe or in the even in the casing also. So due to this blast, okay, this small pressure will be released from the bubbles. The small pressure also keep an impact on the surface of this pipe. So that is going to, so this that is going to make some holes. So small holes will be formed. Okay, the small holes will be formed from that blast. You can write the small holes will be formed, and that small holes is called cavitation. Okay, so our intention is to, what I told you in the starting, we need to avoid the cavitation in the pump. So this is, now see, again cavitation is formed here. So our intention to we should not keep the liquid below the vapor pressure. Okay, so always the pressure should be high, at least if it is less than the atmosphere pressure also, but not less than the vapor pressure value. Okay, so we need to keep the water in such a way so that it should not be boiled. So this is the intention. So this is the cavitation formed here, and this NPSH value will be give us the value of pressure to identify whether it is less than vapor pressure or not. That is the main intention. As I told you that this is very much essential in the pump industry. So now let's find out the value of this. Okay, let me write here. So our vapor pressure is less than, we can write here suction pressure. So suction pressure is nothing but here, this one, suction pressure. Vacuum pressure, what means here the water supposed to be sucked here. So here the suction pressure will be worked here, and this is the HS, the height of this suction pipe here, or head of the, you can say head of the suction. Now this PB in the sense vapor pressure is less than the P suction, which should be less than the P atmospheric. The same thing I have written here, just this one. Okay. Okay. Now let's find out the value of this NPSH from this diagram. So how we'll find out? Now we need to apply the Bernoulli's equation. Now here we'll apply Bernoulli's equation to find out the NPSH value. So NPSH value to okay, before also I have applied the Bernoulli's equation in our last lecture to find out the value. Now here which two sections we need to consider? One will consider this one, like atmospheric value AA, and another one will consider this is the inlet of the impeller, that is inlet of the pump, you can say, that is section 1. Okay, this is the section 1. So apply the Bernoulli's equation between the AA section and 1 section. If you apply the Bernoulli's equation, what? Then we know that the Bernoulli's equation is, as per the Bernoulli's equation, we can write PA by rho G, pressure head, and this is velocity head, V square by 2G, V square by 2G plus ZA equal to, this is the Bernoulli's equation at this level, at this zone. Okay, now which is equal to the Bernoulli's equation at this point, that means total energy at this level equal to total energy other sections. So here I can write same thing, P1 by rho G plus here V1 square by 2G plus Z1. This is the total energy at this point. But when the liquid moved from here, from this point to this point, there is some losses will be there. Okay, that losses will be considered as a HL, the head loss. Some losses are there due to the friction, when the water will flows through a pipe. Okay, so this is the Bernoulli's equation. So this one, let's give an equation number 1. Okay, now if you see in this equation, at this starting point, at this 0, like A level, okay, atmospheric level, the height of this value is, this one is 0, because it started here at this is 0 value, because the water need to replicate from this point to next level. So that's why it is the value distance is 0, and the velocity of this fluid is at this point is, starting point is also 0. But we have some pressure value at the atmospheric value, so that's why we will keep atmospheric value. And so this equation again I'll write in terms of like P1 by rho g. I'll take this P1 one side, and the other term, like here I can write PA by rho g, and this one what, V1 square by 2g. So V1 square by 2g, I'll take it like, I'll write in this way, minus V1 square by 2g, and this is 2g, and this Z1 equal to what? Z1 is nothing but the distance from this center, from this point to here. So the distance from this atmospheric level to up to the inlet of the pump is nothing but HS. Okay, that is the suction head. So in the place of Z1, I can write HS. Okay, and this HL, that is the head loss due to the, here how the head loss will happen when the liquid will flows. So liquid will flows from football and the strainer through this one. So this one we can write HFS. Okay, so this is the equation we can write in this way. Now, okay, this thing also we have discussed in our last previous lecture. If you see, up to this we have done. Okay, the next step is, what will the next step will be there? We need to find out, we need to go for the NPSH. As I told you that NPSH is nothing but, okay, let me write here. So NPSH actually, NPSH can be defined that it is the subtraction addition is there. What is the subtraction addition? So this can be written that absolute pressure. So this can be written the absolute pressure at the inlet condition, absolute pressure head at the inlet condition, minus the vapor pressure head. Okay, minus the vapor pressure head plus the velocity head. So these three things can be added here. That is called NPSH. So what is the absolute pressure head here? Absolute pressure head is nothing but P1 by rho g. This is our absolute pressure head. And what is our vapor pressure head, which is supposed to be minus? That is PV by rho g. So when you talk about the head, so that time we need to consider rho g in the denominator. Okay, only pressure means P1 and vapor pressure means PV. When you talk about the head, then rho g will be divided in this. So this is absolute pressure head, this is vapor pressure head, and the velocity head at this action point, that also need to be added to this one. So this one we can write Vs square by 2g. Okay, so the absolute pressure at the inlet of this point is actually P1 we have to consider. Here it is PA and this is P1. P1 is where? At the inlet of the pump. At the inlet of the pump. That's why I have written here. Now this one I can write equation number 2, suppose. Now what I got here in this previously, if you see this one, this value P1 by rho g, I can put this value of this P1 by rho g in this equation, NPSH equation. So again I can write NPSH equal to this, put the same value here. What I can write here? PA by rho g minus, here I'll do one thing, just I'll open the minus here, so I'll get V1 square by 2g, and this is here, yeah, here we can actually, on place of V1 we can write this is, okay, here actually this one V1 is there, so this V1 is nothing but also suction, okay, that is suction velocity. So that one we can write Vs also here. Similarly here also I can write Vs, suction velocity here. So same thing I'll write here Vs. Okay, and this is minus Hs minus Hfs, and here it is like minus Pv by rho g and plus Vs square by 2g. Now if you see this equation here, I can cancel this V square s, like Vs square by 2g, I can cancel this one, and this 2 point I can cancel it here. So after cancelling, what we'll get here? So we'll get the value of NPSS equal to PA by rho G, okay, PA by rho G minus PV by rho G minus HS minus HFS. So these are the points we are going to get in this after like cancelling these two velocity head. Okay, so now what we can write? This concept we can write in terms of head. So what I'll write here, the next point is NPSH. I can write, now what is this point? PA by rho G. So this is nothing but head, atmospheric pressure head. So I'll write that one in terms of HA. Okay, so HA, this one is what? This one is nothing but HV, or we can write this is HV. You can write HV, this one. Okay, that is nothing but vapor pressure head, then minus HS minus HFS. Okay, so these are the point, like this is the final equation of the NPSS. So this one we can give equation number 3. Again, I'm telling you how I got this H value here. I'll just give a brief about this. Let's keep this one in the side, and here let me write here. We know that we have a equation, pressure equation. So pressure equation we have in the hydraulic law, we found there P equal to, we got there rho G H, pressure. Okay, pressure equal to rho G H. Now here density, this is gravity value, and this is head or height. Now when you calculate the head, H equal to what I can write here? Here I can write P by rho G. Okay, now same thing when I'll try to calculate the pressure, like head, which head? Atmospheric pressure head. So I need to consider the atmospheric pressure at that time. So to calculate the atmospheric pressure head, I can write here small h or capital H, anything we can write here. Okay, so at that point I can write this is P atmospheric by rho G. The same thing I have written here, PA by rho G is HA, that one. Similarly, if you want to calculate the vapor pressure head, so again we need to consider HV, vapor pressure head, equal to, again we need to consider the vapor pressure by rho G. Okay, this is the concept, so that we can find out in this way. So this is our requirement, and we found this one. Now the question is, okay, if you see, so this is our suction head side. If you see, like all this value here, everything is coming here. So this is our suction head. This is our suction head. This is the atmospheric pressure head. This is the vapor pressure head, and this is the losses. This is the losses due to the this foot valve and the strainer. Now here we need to keep some points in our mind. Okay, how to, okay, one more thing is there important. So this NPSH, actually it is two types are there. Okay, one NPSH is available. One is NPSH available, how much NPSH is available and how much NPSH is required. Okay, how much NPSH is required. So two things are there. The NPSH available. So available means we need to find out. And NPSH required. Okay, that required is actually that will be given in the pump by the pump manufacturer. When you purchase a pump, in that outside itself, the box itself, that NPSH required, how much required, that will be mentioned that in that point. So here we'll see NPSH available. So in the NPSH available, let me write here NPSH available. So this NPSH available, it depends on few factors actually. This depends on few factors. What are the factors are there? That actually, what is the atmospheric pressure? I can say what is the atmospheric pressure is there, or we can say what is the pressure in the tank or reservoir. So we can say pressure at tank. This is requirement. This NPSH available, how to calculate, or this is required, depends on this one, first one, the pressure value of the tank. The second one is the liquid level. The liquid level. So which liquid level? The liquid level above the pump. Above the pump. Okay, that is required. And what are the losses during the suction pipe? Okay, during the suction pipe, how much losses are happening? So suction pipe losses, that also need to identify. So these are the requirements are there. Even like another thing, this is most important, the vapor pressure. Okay, the vapor pressure of liquid. This is also important part. Okay, and always keep in mind that this NPSH, okay, the NPSH available, it should be always greater than NPSH required. How much requirement is there? This availability should be more than this required value, so that we can avoid the cavitations. Okay, if it is less than, then cavitations will be formed and very difficult to run the pump. And why, if the cavitations will be formed, as I told you, what will happen? That due to this cavitations happen, it is going to affect the performance, that efficiency, okay, and the performance of the pump is going to be reduced. Many also effect will be there according to this. In the already last lecture, I already detailedly explained. So what is the conclusion we can do here? Like for any kind of pump installation, okay, for any kind of pump installation, that difference between the required NPSS and available NPSS need to be identified. Okay, there should be difference. The value of this NPSH, okay, required will be given by the manufacturer, but the value of this available need to be determined. As I told you, how we can determine by this method. Okay, so available value and NPSS can be calculated from this equation. Okay, this available NPSS can be, this is available, I can do it here. Okay, available, we can calculate from this equation. So if you want to run the pump without any cavitation, okay, or we need to operate our centrifugal pump without any cavitation, then the available NPSH should be always greater than this. This is my final statement. So I hope you understand this lecture. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. I hope you understand. Still, if you are having doubt, means you can give a comment on the comment box. Thank you all.